So now we'll go to Dean. So Dean is also at Manaki Whenua at Lincoln, and he's going to pick up after some of Joe's material. Thanks, Dean.
Kia ora koutou. Joe just told my story more or less, but anyway, hopefully I can add some details.
Sorry, Dean, can I just interrupt you? Can you just turn your camera on so that everyone can see you?
Oh, yeah.
Thank you.
Okay. Hi, everyone. Gosh, hold on. Yeah, that's better. Right, so more on rats, and acknowledgements to Joe and Adrian on this talk. And you've seen a slide similar to this one in Adrian's talk, and that's to show really that rats are so central in forest ecology in New Zealand, and that extends down to predation on birds and how we manage predators and birds. So to understand rat ecology, where do we go? We go to Lake Alabaster, of course. I just got to clear something out here. There we go. No. So yeah, the aim of this, our study here, is really to increase our understanding of rat population dynamics during and following a masting event. And hopefully this will increase our ability to accurately forecast rat dynamics around a masting event and develop cost-efficient management plans. And so we use data from Lake Alabaster that Joe and her team collected, and the site, it was divided into two subsites, A and B. And as Joe just talked about, they were along an elevational gradient from the low elevation sites, which are about 50 meters, the mid elevation, which were about 450 meters, and then the high elevations were, up to 900 meters. And I'm going to show a series of graphs in which the data or the results are organized in this way, with site B and site A with the elevation along the elevational gradients, which is shown here. These are density estimates that Joe got from spatially explicit mark recapture analysis from Alabaster. And again, you can see the A site in the left-hand column here, high, mid, and low, and then the B site, which again, high, mid, and low. And these are the estimated density values, and then these stars are where there were missing data. That there were so few rats captured that Joe was not able to actually get density estimates. So in our modeling, we actually estimate those missing values through data imputation. So there are a few patterns to look at here to start, and the first one is that there is a very high rate of increase in these high elevation sites. They start at very low levels, almost undetectable levels, and increase to relatively high levels, up to 10 rats per hectare, or six rats per hectare in this case. The next pattern to observe is, well, really a lack of a pattern, and that is that there's a variable starting density across the 6 sites, which from a statistical modeling perspective presents a challenge, because there's, quite, in these early months, there's a lot of variability in what's going on across the different sites. And then the last pattern to note before we get into it is that there is a consistent crash following January 2020. And that is very, very similar across all sites, even the high and mid and low sites. And so what we did is we developed a density dependent population model using a Ricker formulation. Oh, I think I left off here, starting to describe our model. And so it's a time varying density dependent model. We allow the density dependence to be high early on because we didn't have data before the masting event to show how it would increase up to the masting event. But we allow it to decrease exponentially after some date, which we fit in the model. And so in our initial, again, I said that we had three basic models that three models that we're gonna talk about here. In the first one, our most basic model, we have the parameters shown here on the left. So population growth, maximum carrying capacity, which is shown by these horizontal lines here, the maximum for low and mid elevation and the maximum for high elevation. And we allowed two different carrying capacities for those two groups, high elevation and mid and low. Preliminary analysis showed that that was appropriate. And then we fit the date of that the decay in carrying capacity begins, okay? And then we fit a parameter that describes the rate of decay of carrying capacity going down. And then we have a starting density because we're fitting an autoregressive model. And then, as I said, we had some missing data, which we fit as well. So if we look at the model predictions against what we observed, and the red dots are what are the density measurements, and this is the mean prediction. The thick line is the mean prediction over time. In this
Dean,
first model, yes.
We've got a presenter view of this, and the words are quite sort of small to read. Can you just zap it up to a full screen?
Yeah.
Super, thank you.
Well, it's not my day, is it?
No, that's good.
Okay, here we go. Yeah, so this is the first model that we did, and if you look at the low and the mid altitude sites, they don't change too much among the different models that we show. They try to predict the varying densities early on, and they fit the crash really well. They won't change too much among the models, but these high altitude predictions will vary across the models. And in this one, you can see that it's over predicting this July measurement a little bit, but it doesn't get up high enough to fit the October or January measurements, especially over here in the B sites where it's this January site isn't even in the 95% confidence intervals. And so what we thought might be going on is immigration from mid to high that would allow this population to grow up at a higher rate than we would otherwise expect just from in situ reproduction. So what we did is we devised a diffusion immigration model, which I'll conceptually describe here. So if this is carrying capacity on the bottom here of the mid sites, which is relatively high compared to the carrying capacity at the high sites, these little dots represent rat density. If you then had an actual density that exceeded the carrying capacity or was at the carrying capacity at the mid site, and you had a low density at the high site, you might expect individuals to diffuse upward. And so we incorporated this sort of diffusion mechanism into our model. And so that required an additional parameter. So we're getting a little bit more complex, this immigration rate down at the bottom. And the results are shown here. Again, focus just on the high elevation sites and maybe just on this B site. You can see early on, there's this pulse of immigration way back in, March or April that pushes the prediction well above the July measurement, but yet it still doesn't get up to the October and January measurements. So our immigration model here is not working quite right. And so what we next explored was a time-limited immigration model using that same diffusion mechanism in which immigration would be limited to start after some date and would finish after some date. And so these boxes sort of illustrate when immigration might start and stop. These aren't the results, it's just sort of an illustration. And we fit a parameter that is the start date and end date. So that goes into our modeling. And again, this is superimposed over the previous results, which showed that there was a pulse of immigration early on. And so we have to make our model a little bit more complex. We add a couple parameters here at the end, and the results are shown here. And if we limit immigration, then we can fit that early July estimate of density, which was very, very low. Immigration pulse starts after that, allows the population to grow to in October and up to January, and it fits the crash very well. This one fits that that July mark really well, the October mark. The January mark is within the 95% confidence intervals, but is still an extreme measurement. And again, these other sites, the data are predicted pretty well, especially the crash. And the crash is predicted well across all 6 sites. And this was our best model as judged by a DIC. And the date at which the carrying capacity began to decay was in late November on average. Okay, so there is some confidence intervals around that as well. And there's quite different carrying capacity levels between high and between the mid and low elevation sites and the high elevation site. So in summary, carrying capacity seems to follow the decline in the resource base following a mast, and it begins to decrease in late November. And the carrying capacity was substantially lower at high elevation sites. And going through these different models showed that to understand the dynamics at high elevation, we really had to incorporate that immigration effect from the mid elevation sites. And the immigration to high elevation was limited in time from August to March, as is shown over here. Now, this was really an ad hoc addition to the model because we saw that just through in situ reproduction, we were not able to capture those dynamics at the high elevation site. I mean, we have a beginning date and an end date. It's not really a mechanistic process, but we don't really have the data to incorporate a mechanistic process into this particular model. We might need perhaps telemetry data over that period to find out when rats would start to move out of a high density area and what direction they would go and how that might relate to environmental conditions such as temperature, for example. And then the last point is that the crash continues right into the following summer. So the model captured the crash really well, but going into the next summer, we might have expected a little tick up of the rat population given that resources might be increasing at that time, but we did not observe that. The rat population stayed really low well into the following summer of 2021 or January of 2021. Okay, so I'll finish with just acknowledging the funding through MB and the data collection, Joe Carpenter's field crew and the Doc Teano office. Thank you.
Great. Thanks very much, Dean. And yep, because of the gremlins, we're going to stop now and take the break that was scheduled. And there will be questions for Dean, if you could send them in, and we'll deal with them at the beginning of the next session. So yep, we're going to take a short break. Come back supposedly 1:45, which is only a couple of minutes away. Maybe we could add a minute to that. Just so a really short break now, and we'll come back soon for session 4. Thank you.